Hello everyone. Last year I produced the ultimate 18650 power bank, which is a huge success thanks to all of you. Since then, I received comments from many of you requesting to purchase this power bank. However, the power bank has several major design flaws, including a complex and intricate wiring surrounding all the modules. And if anything goes wrong, a full disassembly is required to get to the fuse. Even though the 18650 power bank is an awesome project, I still think that I can do better. Thus, I set out to design the best power bank I can that can still maintain all the main features of the last power bank, but it's more efficient, safer, robust, and easier to build, maintain, and customize. And if there's a demand for it, I plan to bring this to the market. Because there are more systems in this power bank, and I want you guys to understand exactly how this power bank works. This is gonna be part 1 of a video series. In this first video, I'm going to go over the electrical system, which includes the battery pack, the control circuits, and the software. And here is the timestamps for this video. Also, I like to mention that I am not a professional programmer nor a professional circuit designer. I learned these concepts over the past few months through research and a lot of experimentation. And this is why I'm excited to announce that the development version of this power bank, which is the version shown in this video, is completely open source. That means that all the links to the design files, bill of materials, code, and purchasing links are in the video description. This way, all of you can improve on the design, and please let me know in the comments if you want a commercial version of this power bank. Also, if you'd like to support what I do, then please consider leaving me a tip on my Thingiverse account. Otherwise, I cannot give out my designs freely forever. And please consider subscribing to my channel if you like my content. Finally, I am excited to announce my first sponsor, JLC PCB. From them, you can order 5 PCBs for just $2, and this project is only possible because of their SMT soldering service. Together with their link to LCSC, the control board PCBs are made as low as $8 each. Furthermore, the service eliminates the need for complicated and tedious SMT soldering and makes the electronics assembly more compact and robust. I'll talk about how to order from JLC PCB later in the video during the control board assembly process. Before going into the circuit assembly process, I would first like to introduce to you all the new features of this power bank. And let's start with its main feature, the USB-C power delivery port, which is capable of delivering up to 60 watts of charging power, which is plenty for every single phone and most tablets and ultra-light laptops. In addition, there are 2 standard USB quick charge ports, and if you forget your cables, the wireless charging is also available on top. As for the design, in this power bank, I took a pretty minimalistic approach. There is a cool 8x16 dot matrix display right underneath the front cover that displays battery percentage, battery status, and output status. When it's not displaying anything, you can't even tell it's there. And of course, just like my previous power bank, this power bank also came with RGB lighting. However, unlike my previous power bank's RGB, which is just to sit there and look cool, this power bank's RGB ring, which is individually addressable, is used to display battery status, indicate charging level, send off warning lights, and can be used as a pretty powerful flashlight. And because all of this is software controlled, it can be used to display some pretty cool effects. And for both the LED and the matrix, you can modify my code and make them display whatever you want. Now I know what you may be thinking, that this power bank is lacking feature compared to the previous 2 power banks, mainly the AC and DC outputs for charging more powerful devices. And this is where I'm going to go into the second main feature of this power bank, the universal expansion port on the side. This port allows you to attach different modules that you can convert the power from the battery into any form you want. For example, you can add a module with a powerful buck boost converter inside that enables you to power anything from LEDs to laptops, cameras, or any other devices that run on DC power. Really, you can create any module to suit whatever you want your power bank to power. And moving on to the battery. Unlike the previous battery pack of the old power bank, this battery pack is fully contained, and the fuse holder is easily accessible. And because the battery can be easily replaced, you can carry as many batteries as you need, and when one battery runs out, you can just swap for another battery. To charge the power bank, you can use virtually anything with a DC output, from micro USB to DC jack to USB-C. The power bank will automatically detect the input voltage and set a charging power based on it. Under a maximum charging current of 60 watts, the power bank can be charged to 80% in just 90 minutes. The power bank also features pass-through charging and automatic charge shutdown, and this leads to the safety of this power bank. This is most likely the safest power bank if built correctly. The internal microcontroller constantly monitors voltage, power, and temperature. If all the software fails, there is also 2 additional layers of hardware protection built into the power bank. With all the features out of the way, let's get into the building of the battery pack. The first thing you're gonna need is the battery. For this battery pack, you can either use 4 or 5 18650 or 21700 batteries. And because these are lithium batteries, here is the warning. Lithium batteries can easily catch fire and explode if mishandled, and the chances of this happening increases with faulty and old cells. Basically what I'm saying is that you are responsible for your own safety when handling these batteries. In any case, all of the batteries have to have very similar internal resistances and have to handle a maximum discharge current of at least 10 amps. I recommend 18650BD or Samsung 50E batteries, as they give a good ratio between capacity and discharge current. The next thing you are going to need is a BMS, which is a battery management circuit. I chose this model because it features 4S and 5S variants and came with overcharge, overdischarge, and short circuit protection. It also features 2 pads on the back for an NTC thermistor, which monitors the temperature of the battery pack. Next, you are going to need a fuse holder, MR30 connector, which is basically a XT30 connector with an extra pin, 2 small size zip ties, and nickel strips that is at least 0.15mm thick and at least 6mm wide, 2 NTC 3950-100K thermistors, M2.5 flathead screws, 18 gauge and 24 gauge wires, and the 3D printed battery pack parts out of either ABS or PETG. Before assembling the battery, measure each of the battery to make sure that they are within plus or minus 50 mV from each other. Place the batteries inside the holder with alternating polarities. Now it's time to connect the batteries together. One way you can do that is by soldering, and I'll demonstrate by using this fake 18650 battery here. Heat up your soldering iron as high as possible. Then quickly tin the surface of the battery within 3 seconds. Likewise, preheat a pre-tinned piece of nickel strip and solder it to the battery also within 3 seconds. This forms an acceptable connection, but because it heats up the battery so much, I don't recommend it. A better way is to use spot welding. A spot welder is somewhat expensive, but if you are connecting a lot of batteries, it is a worthy investment. In any case, clean the surfaces of the battery with isopropanol and connect the batteries in this fashion. Unsolder the appropriate wires leading from each nickel strip, then flip the batteries over and then connect them using nickel strips according to this diagram. Cover the top with electrical tape and solder each individual wires to the BMS. And also connect 2 wires to the bottom of the BMS, leading from the NTC thermistor pads. Here I am twisting on an NTC thermistor. I'm powering on my mini power supply using the battery. As you can see, when I hold the lighter close to the thermistor, the power supply shuts off. The next step is to solder the NTC thermistor and glue it onto the battery using thermal glue, and add an additional thermistor to the other side of the battery pack. This one is for the microcontroller to read the battery temperature. Next, get the top piece of the battery pack, and then glue the fuse holder into its socket. Then thread the 3 remaining wires into an opening near the tip. They should be the positive and negative of the battery, and the remaining wire from the thermistor. Next, close the cap, secure it in place with screws on 4 sides, and then cut the wires, and solder an MR30 connector according to this pinout. Then glue the connector onto the battery pack. For the pull tab, first insert zip ties into the battery pack, and then slide in the 3D printed pieces. Add 2 magnets, one to the battery pack and one onto the corresponding centerpiece, and glue them in place. Make sure those 2 magnets attract each other and do not repel. Slide in the last piece of the pull tab into the slot, trim the zip tie, and then super glue them in place. Finally, add a micro 10 amp automotive fuse into the fuse holder, and the battery pack is now complete. You can test the fit by adding a female connector to the power bank body piece, and then sliding the battery pack in to see if it fits. If the action is too stiff, you might want to squeeze the pins on the female connector. Don't squeeze it too loose, as we want some amount of resistance for a good connection. Since we are only passing less than 10 amps for a 30 amp connector, it doesn't really matter if the mating force is a bit lower. Now let's move on to the main control board assembly. And to start out, I'll explain how the overall circuit works. And again, the circuit diagrams and the Gerber file are in the description, along with the Easy EDA design file. The microcontroller chosen for this power bank is the classic Atmega 238P, which is featured on the Arduino Nano, Pro Mini, and Uno models, so you can program it with the classic Arduino IDE. First, I'll explain the on-off system of this power bank. The microcontroller and all its supporting components takes around 300 mW to operate. This will cause the battery to be completely drained within 12.5 days. One way of reducing power is to put the microcontroller into sleep, but because of all the complementary components and sensors, there is still too much power draw, so the best option is to cut the power completely. And to do this, I am going to use a mini DC to DC step-down converter, and this particular model is special as it has an enable pin. And by connecting it to ground, the output of the converter can be disabled, which reduces the power draw to less than a milliamp, which makes the battery last easily over a year without charging. And with a combination of a push button and a 5V regulator, we can keep the microcontroller turned on as long as the button is pressed. But this is not what we want, as we have to always hold down the power button in order for the power bank to operate. So we can connect another digital pin to the enable pin of the step-down converter. This way, as soon as the microcontroller turns on, we can send a digital output to pull the pin high, so the microcontroller would always stay on. And as soon as the signal drops, the power bank turns right off. As for the different sensors, this power bank has a total of 9 different voltage, temperature, and current sensors. To save on the pins, we are going to use this HC4051 analog multiplexer. This multiplexer takes one analog signal and splits it off into 8 lanes. And here are the sensors. 4 different temperature sensors, which are just 100 kΩ NTC thermistors. One for the battery, one for the charging circuit, one for the module, and one for the output circuit. And 2 voltage sensors, which is just a simple voltage divider. They are responsible for reading the battery voltage and the input voltage. And finally, there are 2 20 amp Hall effect current sensors, and they are responsible for reading the input and output current of the power bank. Additionally, there is one limit switch here which detects whether a module is connected securely. Now, there are 4 MOSFETs, one for turning on the output circuit, one for turning on the module, one for turning on and off the relay that controls the charging circuit, and finally one for turning on and off the fan. There is also another mini DC to DC step-down converter powering the wireless charging circuit, and it is also controlled via a digital signal using the enable pin. A digital potentiometer is used to control the charging current in this power bank. This potentiometer does exactly what it sounds like. It replaces the trim pot on the constant current step-down converter, so instead of needing to be turned by hand, the resistance can be controlled through the software. The WS2812 LEDs are controlled through the digital pin, and the LED dot matrix is controlled through I2C. Now this is basically how the power bank circuit is connected. If you have any questions, please review the schematic down in the description, and if you're still puzzled, you can ask them in the comments and I'll try my best to answer them. I am also letting you know that I am not a professional circuit designer, as I've learned how to design circuits through trial and error in the past few months. So if you could improve on my circuit or offer suggestions, that would be greatly appreciated. With all that said, let's get to actually building the circuit. After you download the design files, there should be a Gerber design file, a bill of materials, and a pick and place file. Now go to JLC PCB's website and click on the Order Now button. Add your Gerber file and select 2-layer PCB, 35 ounce of copper at 1.6 mm thick. Leave the rest of the options as default and scroll down to the SMT assembly section. Now add in the bill of materials file and the pick and place file. After uploading the files, JLC PCB would ask you to confirm each component. For me, the order arrived in just 5 days, and as you can see, all the PCBs are in pristine quality. Now the first step is to test the microcontroller to make sure it works. Now you can see a row of pins labeled 5V, ground, RX, TX, and DIR, which is just like an Arduino Pro Mini, which means that you'll need a FT232 adapter to program this. But we actually cannot program this just yet. Because this is a brand new chip from the factory, it does not have any bootloader on it. So the first step is to flash the bootloader. I won't go into details here, as there are many tutorials on YouTube of how to flash a bootloader, and the corresponding pins are right next to the buttons. After you watch how to flash an Arduino bootloader tutorial, you can just stick the corresponding pins into the corresponding holes and apply pressure onto one side of the pins to provide a good connection, and click the Flash Bootloader button. Now you can program the chip just like any other Arduino Pro Mini via the FT232 adapter, and then test the board by uploading the main code and see if anything shows up on the serial monitor. If you get anything like this, congratulations, the circuit is most likely working. Now you will need to solder in all the through-hole components. As a reminder, the bill of materials is in the description. Now solder in the 4 push buttons, but one thing to be aware is that we do not want anything protruding to the other side. So cut the leads short and solder them from the top. Next, solder on the 2 IRLZ44N MOSFETs. The next component is the relay, and this particular model is JFC21F4100, which is a 5V relay that can handle 3 amps. The next step is to solder on the DC jack. This particular DC jack is rated for high current, but you need to remove the bottom 2 pins to leave room for the micro USB connector. After soldering on the DC jack, you can carefully solder on a micro USB connector, although this is optional. Next, connect 2 pins to the USB trigger. I am using a 20V version for maximum power. In any case, solder it onto the silkstring outline and glue it in place using thermal glue. Flip the board to its back and locate the 2 pads labeled case temp. Push a thermistor into the pads and solder it in place. Now take the USB quick charge module, solder 2 pins to it, and cover the back using Kapton tape. Then push it into the corresponding holes labeled QC-VCC, and then glue it in place. Now you can repeat the same process to the 2 mini DC to DC step-down converters. Solder header pins to them and adjust their voltages to exactly 5V. Remove the header pin plastic, cover the back using Kapton tape for insulation, and then glue them onto the PCB using thermal glue, and solder them in place. Repeat this for the step-down converter on the other side also. Next, locate 3 holes around the middle of the PCB. Now push in an M3 screws from the top and secure them in place with a nut. Then, cut a piece of silicone thermal pad and stick it in between the 3 screws, and carefully lower the USB PD module in place and secure them with 3 more nuts. Now, locate this pad on the top of the board and solder a 18 gauge wire to it and loop it through one of the MOSFET holes onto the positive of the USB power delivery module. There is no need to connect the ground pad to anything, as it is already connected via one of the screws on the back. Now, between the 2 pins on the back, in order for the power bank to function, they need to be shorted. This can be done either with a wire, or better, with a 70 degrees normally closed temperature switch. This way, whenever the circuit temperature reaches 70 degrees, it will automatically shut off the power bank. Cover the switch in Kapton tape to prevent anything from shorting out. The next major step is to modify the buck boost converter with constant current. First, remove all the screw terminals and the constant current potentiometer and replace them with wires. desolder the voltage potentiometer and lay it flat, and then insert an NTC thermistor into the heatsink and secure it with thermal glue. By the end, your converter should look something like this. Now, attach 10mm brass standoffs to one side of the converter and add a piece of silicone thermal pad onto the top of the heatsink and push it into the two corresponding holes on the main control PCB. Secure the standoffs in place with M3 nuts. If you do not have brass standoffs, long screws and nuts also work. Next, locate the 4 holes on the corner of the PCB and connect 2 pairs of input and output wires according to this diagram. Connect the wires from the NTC thermistor to the 2 pads labeled charge temp. Next, locate the 2 pads named X9C. Since both through-hole and SMT versions of this IC exist, I made it so that you can use either one. Whichever version you use, solder it onto the PCB and pay attention carefully to the orientation dots. If you would like to forgo the X9C digital potentiometer, then you can just extend the constant current potentiometer wires and adjusting for a constant current. I recommend 1.2 amps. To complete the converter installation, solder the 3 wires from the potentiometer to the PCB. The pad labeled H is the pad furthest away from the potentiometer knob. Solder the 5V fan onto its corresponding pads, and then take the limit switch, bend the pins and solder it onto this orientation. To test the whole circuit, solder on the LED dot matrix to the 4 pads right next to the chip. Now get the WS2812 LED ring and solder 5V ground and signal wire to it, and solder them onto the corresponding pins right next to the buttons. Next, desolder the USB port of the wireless charging module. Because these pads are really tiny, I am going to use instead the large filter capacitor as a connection point for the power wires. Solder 2 wires, one to the ground and one to the wireless VCC. Instead of soldering the wires directly to the board, you can also use 2.54mm Molex connectors. They make the power bank easier to assemble later on. However, they are optional. And with that, the control circuit is pretty much complete. Now hook up the control circuit to the battery via the ground and VCC pads near the back of the PCB. Hook up the FT232 to the PCB and upload the code. On the serial monitor, you will see a block of numbers that will come every second. The first value is the battery voltage. Now, measure the voltage of the battery using a voltmeter and check if it matches up with the value printed on the serial monitor. It is crucial that this value is extremely precise. So if it doesn't match up, then go to the voltage divider section near the top of the code and then change the value of the 47 kΩ resistor up and down slightly, and upload and check again until the voltage is exactly right. Then, test all the functionality of the circuit. There is a short checklist in the design files, and you can go through a checklist to make sure that everything is working as it should. If everything is working correctly, congratulations, you are done with the most complex part of the build. In the next video, I will show you how to put everything together and how to make custom modules for this power bank. The next video should be up within 3 weeks. And until then, thanks for watching.